Hello, bonjour, bienvenue, and welcome everyone to Perimeter Institute's public lecture series. My name is Emily Petroff, and I'm Perimeter's Director of External Relations, and I'm delighted to welcome you back for another exciting PI public lecture. In its very mission, Perimeter Institute was designed as a place to gather and connect, where we can come together, like we are doing tonight, to ask the big questions about the universe and search for the big answers. This year, we are celebrating Perimeter Institute's 25th anniversary. 25 exceptional years of bringing people together from all paths, researchers, students, teachers, and the general public, to explore the fascinating world of physics. But people on this land have been asking big questions about the universe for thousands of years. The quest to explore the world around us, to piece together our origins and understand the building blocks that make our world, these are all human constants throughout the ages. We acknowledge that both Perimeter and the building we are in tonight are situated on the traditional territory of the Anishinaabe, Haudenosaunee, and Neutral peoples. And Perimeter is located on the Haldimand Tract, the tract granted by the British to the Six Nations of the Grand River and the Mississaugas of the Credit First Nation. We acknowledge and thank the many peoples who have preceded us and share this land with us, and we commit to moving forward in a spirit of reconciliation, to acting responsibly and collaboratively to advance the quest for knowledge for the benefit of all. So I hope you will join us in this endeavor tonight and all throughout our 25th year. And by the end of tonight, I hope you will leave this talk having learned something new and met some new people. We'd like to also take a moment to say thank you to the people who make events like these possible. Thank you to all of our supporters who help us to engage and inspire young minds, train and support educators, share science with the general public, and help bridge the knowledge gap in science. If you would like to join our growing community of friends and supporters, you can visit our website to learn more. We would also like to extend a special thank you tonight to the Center for International Governance Innovation for hosting this special lecture. For those watching the live webcast, please join the conversation online, either through the YouTube comments section or connecting with us as Perimeter Institute on Instagram. If you have a question for our speaker, you can ask it with the hashtag #PILive. And now, it is my very great pleasure to introduce tonight's speaker. Dr. Katie Mack is a theoretical astrophysicist and science communicator extraordinaire. She completed her PhD at Princeton University in the United States, researching the physics of the early universe. She then went on to work as a postdoctoral research fellow at the Kavli Institute for Cosmology in the UK, followed by an appointment at Melbourne University as a Discovery Early Career Research Award recipient. In 2018, Dr. Mack joined the faculty at the North Carolina State University. She was appointed as a Simons Emmy Noether Fellow at Perimeter in 2020 and officially joined the faculty at Perimeter in 2022. She holds the Hawking Chair in Cosmology and Science Communication at Perimeter. Dr. Mack's research spans a range of questions in cosmology, from models of dark matter to vacuum decay to cosmic dawn and the physics of the early universe. For over 10 years, Dr. Mack has also been doing extensive science communication as Astro Katie, and through her popular science writing for outlets such as the BBC, Cosmos Magazine, the New York Times, and the Globe and Mail. Her first book, The End of Everything, Astrophysically Speaking, published in 2020, was a New York Times Book Review notable book and is now available in over 15 languages. Dr. Mack is also the host of two 10-part explainer series, Quantum 101 and Cosmology 101, available now on the Perimeter YouTube channel, and co-hosted the podcast The Universe with author John Green. Tonight, she will tell us about the cosmological quest to understand the history and fate of the universe that we live in. Please join me in welcoming to the stage Dr. Katie Mack.
Hello. I'm delighted to be here. I'm so glad to see all of you here. This talk has been a long time coming. It was supposed to happen last year. It's happening now. I'm so glad that you've come. I am very excited to talk to you today about the end of the universe. It's one of my favorite subjects. But before I get into that, with talks like this, when we're talking about something really heavy, I like to start with a little poetry. Some say the world will end in fire, some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. That's the famous poem by Robert Frost from 1920. Of course, now we know the answer. It's fire. The world will end in fire. In something like 1 billion years, the sun will be so hot and bright and swelling out that it will boil off the oceans of the Earth, leaving the Earth a charred and lifeless lump of molten rock. So, fire, done. But as a cosmologist, I'm interested in the bigger questions. I'm interested in what's going to happen to the universe. I mean, we might leave the Earth, we might go somewhere else. Maybe when the Earth is charred and lifeless and empty, there will be somewhere else to be. But the cosmos itself also has a fate. And today I will talk about some of the possibilities for that. I'm going to go into 4 different possibilities tonight. There's an extra one in my book, just so that you know something else to look for. But tonight I will talk about the Big Crunch, the heat death, the Big Rip, and my personal favorite, vacuum decay. So before we get into the destruction, let's kind of orient ourselves so we're all on the same page where we're at right now. So we live in a galaxy called the Milky Way. This is a picture of the Milky Way galaxy from the inside, where we are. This is actually an image from the southern hemisphere, which is the best place to look at the Milky Way, because in the southern hemisphere, you can see the core of the Milky Way, and that's what this is here. It's a spiral galaxy, it's a disk-shaped galaxy, and if we were able to be outside the Milky Way, it would look kind of like this. This is actually our nearest neighbor large galaxy, the Andromeda Galaxy. You can see it has a central bulge, it has spiral arms, it's shaped like a disk. There are something like a couple of trillion galaxies in the observable universe. When we point our telescopes out into space, like the Hubble Space Telescope, we see galaxies everywhere we look. This image is from the Hubble Space Telescope. It's called the Hubble Ultra Deep Field image. And for this picture, they pointed the telescope at one fairly empty spot in the sky for about 11 days, and they found something like 10,000 galaxies in the picture. If you look at this picture, there are a couple of little spots that are actually stars that got in the way, stars in our own galaxy. You can usually tell them because they have these diffraction patterns, these diffraction spikes. But pretty much everything else in this image is a galaxy. There's a little spiral galaxy, there's edge-on disk galaxies, there's elliptical galaxies, there's sort of fuzzy ones, there's a cute one down here. There's just trillions of galaxies out there in the cosmos. And there are a few things that we learn by looking at images like this and taking this data. One thing that we learn is we can learn about the history of the cosmos. So it turns out that when you look at distant things, you're looking into the past. This is probably something you've heard before. If you look out at the night sky, you're looking at stars, and the light from those stars has taken a long time to get to you. For the stars in our Milky Way that you can see at night, it might have taken tens or maybe hundreds of years for the light to reach you. If you look at the sun, you're looking at 8 minutes ago. Of course, you should use proper eye protection if you do that. If you look at the moon, you're looking at 1.3 seconds ago. If you look at some of these distant galaxies, you could be looking at billions of years in the past. And just to be clear, it's not just things in space that are delayed like that. Every time you look at anything, you're looking at the past, because light takes some time to travel. So if it turns out that light takes about a nanosecond to travel about a foot. So just in this room, if I look at the front row, I'm looking at people who are, from my perspective, maybe 20 nanoseconds in the past. In the back row, I don't know, 150 nanoseconds in the past. So all of you are in the past, as far as I'm concerned. Everything you see is in the past. But with images like this, we can look deep, deep into the history of the cosmos. Our universe is, as far as we know, about 13.8 billion years old. And some of the images in this picture, some of the galaxies in this picture, are from the first few 100 million years of the cosmos. So that's one thing that we learn by looking at pictures like this. The other thing we learn is that the universe is expanding. When we look at distant galaxies like this, there's a weird thing that happens, which is that the distant ones all kind of look redder than they should. And what's happening there is that as the universe is expanding, the light of these distant things is getting stretched out by the expansion of the universe. And when visible light gets stretched out to longer wavelengths, it goes to the red part of the spectrum. If you look really far away, you can see things that are stretched out into the infrared part of the spectrum, which is why James Webb Space Telescope looks in the infrared. So every time we look at distant galaxies, they all look red because the universe is stretching out. They all seem to be moving away from us. It's not just that we're really unpopular, it's that the universe is expanding in kind of all directions. And so, if we're in one of these galaxies here, as the universe gets bigger, this is my very sophisticated animation, the other galaxies get farther away from us and farther away from each other. There's more and more empty space as time goes on. And so we can see that the universe is expanding, and we can see that when we look far away, we're looking at into the distant past. And this is really the basis for the Big Bang theory. The Big Bang theory is the idea that the universe is expanding now, things are getting farther away from each other, the universe is getting less dense in the sense that there's the same amount of stuff, but more empty space. And so it stands to reason that in the past, things were closer together. The universe was more dense. The universe was hotter because there was more stuff, more energy packed into smaller space. And so just by using the fact that the universe is expanding now, we get to the idea that in the very distant past, in the beginning of the universe, it was small and hot and dense, small in some sense. It may have been infinitely large, and it's been getting larger. That's a thing that could happen, I'm sorry. But it was in some sense smaller, things were more compact in the past. That's the Big Bang theory, that's the essence of that idea. And so we can start to draw kind of diagrams of sort of what this would look like if you could kind of see it from some other perspective. So, we're here in the modern universe 13.8 billion years after whatever the Big Bang was. And as we look farther into the distance and into the past, we can see things like the Hubble Ultra Deep Field that I showed you is looking at things that were around the 500 million years in the age of the universe. But then, you kind of look farther and it's like, well, at some point, you should be able to see a time when the universe was extremely hot and extremely dense and filled with plasma, because if you just dial that expansion back, you get that everything is compressed into smaller spaces. Everything is compressed and hot and full of this energy, right? And we call that the radiation era, and it's depicted here. And you might wonder, why don't we see that? When we look out into the night sky, it's dark, it's not fiery, right? Except it actually is. We just can't see it with our eyes. So because the universe has been stretching out, if we look far enough away, we are looking so far into the past that we are seeing the time when the universe was hot and dense, but the light has been stretched out by the expansion of the universe into a different wavelength, one we cannot see with our eyes. It's stretched out into the microwave part of the electromagnetic spectrum. So, if you go farther, longer wavelengths than infrared, you get to microwave and radio, and that's where the light from that early universe is. And so we can actually see, if we look in any direction far enough, we can see light that has taken so long to get to us, it's traveled from so far away, that we are seeing the universe as it was in the very beginning. And that's called the cosmic microwave background. And I'm going to show you a couple of depictions of the cosmic microwave background. The first thing I'll tell you about the cosmic microwave background is that it looks basically the same in every direction. And as long as you don't stretch the contrast too much, basically it looks like this. Okay, so this is an all-sky picture of the sky and the microwave part of the spectrum, where I've colored microwaves of that frequency purple, just so you can see them, because otherwise it would be a very uninteresting slide. And so we see this background light. It's all about the same color. It's everywhere in the sky. And we interpret that as the glow from the early universe. And you might wonder, how do we know for sure that that's what we're looking at? Well, one thing that we can do is we can look at that light and we can take a spectrum of that light. We can put it through a prism. We can see how much of the light is at different wavelengths, different frequencies in the microwave part of the spectrum. And I'll show you this is what the spectrum looks like, roughly. So on the vertical axis, that's the intensity of the light. Horizontal is the frequency. So basically you're saying that most of the light is at that sort of purple frequency that I showed you, and then there's a little bit less at the redder part of the microwave spectrum, and a little bit less at the purpler part of the microwave spectrum. But it goes like this. So there's a kind of peak, and then it drops off. And in this graph, the sort of diamond shapes, the dark squares there, those are the data points. So that's the data from just taking the spectrum, looking at the intensity at different wavelengths in the sky. And the sort of gray bars are the uncertainty on that measurement. Basically, no measurement is perfect, so there's some range that we think the true measurement is somewhere in there. Except in this plot, in order to be able to see the uncertainty at all, I had to magnify it by 400 times. So it's a really extremely precise measurement. And the line that's passing through, this curve here, is a very special kind of line. It's called a black-body curve, a black-body spectrum. And the black-body spectrum is the spectrum of what we call thermal radiation. It's the kind of radiation that occurs when something is warm, when something is hot. The particles are bouncing around, and they emit light just by bouncing around, just by thermal motions. It's the light that you get if you take a poker and you stick it in a fire and it gets hot and it starts to glow. That's black-body radiation. The cosmomicrowave background, as far as I know, is the most perfect black-body ever measured in nature. I think even ever measured in a laboratory. So what that's telling us is that when we look out into the sky in every direction, if we look far enough, we see light from a universe that is glowing because it's hot. That's what black-body radiation is. It's the light you get from something that's glowing because it's hot. So what that tells us is that in the very early universe, the whole universe was full of this plasma, and the whole universe was dense and hot and glowing with heat. So if we take that picture again and we stretch the contrast, and we have to stretch it a lot, we have to look at one part in about 100,000 differences in the frequencies, we get that there's some structure here. We get that there's some places where the universe was a little bit hotter or a little bit colder in that early time. And we can get better and better measurements over time. This is a fairly old one. This is from 2003, where you really start to see those hot and cold spots in that background light. And this is the more recent one. This is kind of the best picture we have of the cosmomicrowave background light. And what we see in this is we see regions where there's like a little bit more plasma, a little denser in some places, a little less dense in other places. And what we can do is we can look at that and we can take that information, put it into a computer model, and say, what if you have a universe that's full of plasma that has a little bit more over here and a little bit less over here, and you just let time go on and gravity pull stuff together, and what you get at the end is clusters of galaxies. So we know how that evolution happened. We know how these little fluctuations grew into clusters of galaxies and sort of populated the cosmos with all the structure we see today. Technically speaking, these fluctuations are actually the result of sound waves. So they're called acoustic oscillations. One thing to know about the early universe was that it was hot and dense and loud. There were pressure waves moving through it. I won't get into the details of it, but one of the things we can do is by looking at these patterns and looking at how those sound waves are moving around, we can learn about what the universe was made of at the time, just like you could use how sound moves through an object to learn about what that object is made of. And we can learn about sort of everything between here and there. Everything else in the observable universe is between us and the cosmomicrowave background, because we can use it as a backlight to learn about the structure of the cosmos. And we can use it to learn about the future of the cosmos by understanding how the universe evolved from that to what we see today. That brings us to our first end of the universe scenario, the Big Crunch. So the idea behind the Big Crunch is fairly simple. The idea is the universe is expanding now. What if, at some point, it starts to recollapse? This is an idea that's been around for a long time. In the 1960s, it was the favored idea for how the universe would end. Basically, what's happening is that the universe is expanding. That expansion was kicked off by the Big Bang. But, all these galaxies are kind of pulling on each other with gravity, right? So if the expansion isn't strong enough or the gravity is too strong, then the expansion will stop and reverse, right? Things will start to come together again. And you might wonder what happens if the universe starts to come together. We would start to see that galaxies would be moving toward us instead of moving away from us. Instead of being red-shifted, they would be blue-shifted. So that would be interesting. The light would be moving toward shorter wavelengths or higher frequencies as time goes on. At some point, the universe would start to get kind of crowded. The space between galaxies would become less. And at some point, the galaxies would start to interact with each other. We would have galaxy collisions or galaxy mergers. And we actually see galaxy mergers in the cosmos all the time. This is not an uncommon thing, not because the universe is imminently collapsing, don't worry, but because galaxies tend to be born in groups or clusters, and so if they're already kind of close together, then the mutual gravity can bring them together into a collision. And so we see things like this out in the cosmos all the time. This is an image called the mice. It's a pair of galaxies where they're colliding with each other, and you can see a few things happening here. There are these long trails. That's why they're called the mice, because they have the tails. They're called tidal tails. And these tails are stars that have been sort of flung out by the tidal forces of the collision. The gravity gets everything kind of mixed up, and you get these long streamers of stars coming out. And we have entire catalogs of galaxy collisions, galaxy mergers. We call them train wrecks. And in these, you see a lot of these tidal tails coming off. You also see things like sort of red and blue bunches of stars, little clusters of stars, and those are because when galaxies collide with each other, the gas within the galaxies kind of gets compressed, and that can cause bursts of star formation. So you get these bursts of star formation, so you get all these hot young stars, very massive stars that then burn out really quickly, but they're really bright when they happen. And so you can see that, and then when they burn out and cause supernovae, then they create a bunch of dust, and so you can see sort of dust lanes stretching across some of these images. And it's kind of a big cosmic light show when these collisions happen. And we're going to get a front row seat for that, because in about 4 billion years ago, the Andromeda Galaxy is coming for us, or in 4 billion years from now. So this is the Andromeda Galaxy, which I showed you before. It is our newest neighbor, and it is coming for us at about 110 kilometers a second. It's currently pretty far away, so it'll take a while to get here. But the best guess that we have right now is that in something like 4 billion years, it'll either collide with us directly, or it'll kind of loop around and probably come back again later. But it is moving in our direction right now. And there was a study a few years ago where astronomers were simulating what that would look like if we were here to see it. Now, to be clear, we will not be here to see it. Okay, 4 billion years is long past the billion years at which point the Earth is dead. But, we might leave like a webcam or something. Like we could, it would be really neat. So let's, kind of go through what it would look like. So this is a depiction of the sky today with the Milky Way, and that's Andromeda right there. And so if we fast forward to 2 billion years from now, it's getting bigger. 3.75 billion years, it's coming even closer, and then, oh no, things are happening. You can see those bursts of stars. It gets messy. We probably wouldn't have that much star formation happening because we don't have, by that time both us and Andromeda would have used up a lot of our gas, but it would, you get something, so it get mixed up and then it would kind of come around for, loop around, you start to get those tidal tails forming, which is really cool. And then after about 5 billion years, the stars are starting to burn out, the ones that were formed in the collision. And then by about 7 billion years, you have an elliptical galaxy with just not a whole lot going on in it. And apparently we're supposed to call that Milkdromeda, which I don't think is a very inspiring name for a galaxy, but anyway, that's what we'll be in about that time. And it's not because the universe is collapsing, but it's just because Andromeda is already nearby and it's already coming for us. But I should say that being in a galaxy collision is not necessarily a death sentence, right? When galaxies collide, even if they collide, head-on, really, directly, it's very unlikely for individual stars to hit each other. The stars tend to be sort of pretty well separated in galaxies. There's a lot of empty space in terms of space between stars in galaxies, and so the chance that any two stars would actually collide is pretty small. So if you were living on a planet orbiting one of these stars during a galaxy collision, you might end up, flung out on one of these tidal tails. Your neighborhood looks a little different, but the chance that you're actually going to be colliding with another star is pretty small. You could get fried by nearby supernovae, or when the supermassive black holes in the centers of the galaxies collide, they could create big bursts of radiation that could also kill you. But generally speaking, it's not necessarily the end of the world. Our world, again, dead, but the end of some hypothetical other world. So, in a big crunch scenario, it's not the galaxy collisions that kills the stars. There's something else that does that. So, I mentioned that as the universe is collapsing, the galaxies start to get blue shifted, right, as they're moving toward us. Turns out all of the light from everywhere in the cosmos is going to be blue shifted. It's going to be shifted to harder radiation. So that cosmic microwave background light that I talked about is going to be shifted toward the infrared, toward the visible, toward the ultraviolet. The light from stars, from every star that's ever shown in the universe, is going to be shifted to ultraviolet, to gamma rays, X-rays, or X-rays and then gamma rays. It's going to be shifted to harder radiation, and there's going to be more of it compressed into smaller space. The universe is going to get very hot and very uncomfortable. And even hotter than sort of a similar stage in the early universe, because in the early universe, the universe was full of plasma and then it was cooling. But in the time since then, we're not just sort of dialing that back. We've had all these stars shining, and those stars have been creating a lot of hard radiation, and that radiation is added onto it. So in 1969, an astronomer named Martin Rees, who until very recently was the Astronomer Royal of England, wrote a paper about the Big Crunch, because that's what was expected to happen. He called it The Collapse of the Universe, an eschatological study. And he went through exactly what you would see if you were in the Big Crunch, which is terrifying, because they thought that was actually coming at the time. Not for a while, but and what he found was that when the crunch is happening, when the universe is compressing, there's so much ambient radiation in the universe. The universe is so full of this hard radiation that the radiation can actually ignite the surfaces of stars in thermonuclear explosions. And that is unsurvivable. So, personally, I find the idea of a big crunch absolutely terrifying. I think that it would be very uncomfortable. I do not like it. Fortunately, the more likely end of our universe is something called a heat death. And the reason I use a snowflake as the emoji for this one is that the heat death is actually a very cold kind of ending. The term heat there refers to sort of disordered energy. It refers to how entropy is moving through the universe, and I'll get into that in a minute. But it's not a hot death, it's a really very cold one. It's sometimes called the big freeze. And it takes a really long time. So the idea behind the heat death is, what if the universe just keeps expanding? And the reason that we think that this is more likely at this point is because in the 1990s, astronomers were trying to figure out, is the universe going to keep expanding forever, or is it going to collapse? The question was, as the expansion is happening, is there so much expansion that it just keeps going, or is there enough gravity from all the galaxies that by sort of putting on the brakes, by slowing down the expansion, they can stop it and have it come together? And that was the question, is this sort of balance. It's kind of like, very similar to like if you take something and you throw it up into the air. Like imagine that the throwing up into the air is like, this is the Big Bang is the push, and then it's moving outward, but the gravity of the Earth is pulling on it, its gravity is pulling, so it makes it always slow down, right? As after you throw something into the air, it's always slowing down, it's decelerating. And generally speaking, you throw it up into the air, at some point it stops, and it falls back down. And that would be sort of a big crunch. If you were really strong, if you could throw it really fast at 11.2 kilometers a second, escape velocity of the Earth, then it would not come back, right? It would be slowing down, but it would reach, leave the Earth, and it would not return to you. And if you throw it much faster than that, it'll keep going, but it'll always have that sort of slowing because the Earth is pulling on it, because gravity does that, right? It causes this deceleration. So astronomers were looking at the expansion of the universe. They were measuring how quickly galaxies were moving away from us and how that has been evolving over time. And they wanted to measure the deceleration parameter. How quickly is the expansion of the universe slowing down? Because if the deceleration parameter is big enough, then we're fated for a big crunch. If it's not, then we'll keep expanding forever. And so they went ahead and measured it, and they found out that it was a negative number. They found out that the universe was not decelerating at all, that the universe was actually speeding up, which is about as weird as if I take this and I throw it up into the air, and it slows down for a little bit and then just shoots off into space. Clearly, I have missed something in my equations. I thought that the only things that could happen were that it would slow down and maybe stop, slow down, and keep going, but instead it slowed down for a little bit and then accelerated away. If you do that with throwing a ball into the air, you can imagine maybe there was like a big wind, maybe somebody had put little rockets on the bottom of your ball, but there's some extra physics that you did not include in your equations, right? And so at the time, it was a big surprise because they thought, well, gravity always pulls, and there's nothing else going on on these scales. It's really just gravity and motion. But there was a concept that was kind of floating around that was originally written down by Einstein called the cosmological constant, which is this idea that maybe every little bit of space has a little bit of kind of stretchiness built into it. And as the universe gets bigger and bigger, that little bit of stretchiness starts to kind of push and create the acceleration of the universe. Just to be generic, they called whatever is making the universe expand faster, they call it dark energy. And we still don't know what dark energy is. There are lots of questions about what dark energy is, especially lately. Most of the data does fit the idea that it is a cosmological constant. I'll get more into what the cosmological constant really is in a moment. But most of the data fits the idea that it's just a sort of a property of space itself, that space has this little bit of stretchiness built in, and as there's more and more space, there's more of that stretchiness, and it creates that acceleration when the universe gets big enough. If that is the case, if it is a cosmological constant just built into the physics of the universe, then we know what's going to happen. The universe is going to keep expanding. It's going to keep accelerating in its expansion. And we know how that's going to go. We can calculate out how that's going to go. Over time, the universe will get more and more diffuse. Galaxies will get farther and farther apart. There will be more and more empty space. The universe will get colder and darker. In about 100 billion years, we will be in a situation where we cannot see other galaxies. So if this is Milkdromeda, our single leftover galaxy, we will not see any others. You could put the Hubble Space Telescope into the sky in 100 billion years, and it will see nothing but darkness. It'll see maybe a few of the remaining straggler stars in our own galaxy, Some of the stars in our own galaxy will last more than 100 billion years, not all of them, but some will. But we won't see other galaxies because they'll just be moving away too fast. Their light will be so redshifted that we will not be able to see them. In 100 billion years, we won't be able to see the cosmic microwave background either, because the light will be stretched out so much that we won't be able to distinguish it from just sort of random fluctuations of radiation in the universe. In 100 billion years, we'll have no evidence that the universe is expanding, no evidence that there have ever been other galaxies. We'll be living in a galaxy with some dying red stars. Over time, there will be no new stars being formed because it takes gas to form new stars, and our galaxy will have used up all the gas that it had to form stars, and there are no other galaxies coming in to bring new gas to form new stars. So the stars that we have will burn out. Some will create black holes. The black holes, some of those will merge together, and then the black holes themselves will start to evaporate. It's a sort of quantum process where a black hole can kind of shrink by releasing a little bit of radiation. The black holes will evaporate, and then whatever matter is left over, the matter will start to decay. We don't know for sure if protons themselves can decay, but we know that the other particles can, and if protons decay in something like 10 to the 34 years or more, those will start to fall apart, and eventually, after a very, very long time, the universe will be left cold, dark, empty, lonely place. And at some point, all the radiation that's gone out from all the decay of everything will be so diffused, and everything will have decayed into total disorder, in the sense that when we talk about the evolution of things in the universe, we talk a lot about the second law of thermodynamics, which is this idea that entropy, disorder, just increases into the future. At some point, the entropy will increase so much just from everything decaying into the waste heat of everything that ever existed, that we'll reach kind of this maximum entropy state where nothing else can really happen because we've already got to the maximum entropy state. And if the future is where entropy is increasing, entropy can't increase anymore. And that's the ultimate heat death of the universe. The universe is cold, dark, empty, lonely, and essentially nothing ever happens again. It's a sad story. On the bright side, it could be worse. So, the Big Rip is a story about what happens if dark energy goes really, really badly for us. So we know that dark energy is out there because we know that the universe is accelerating. There has to be something else besides just the normal gravity, the normal evolution of space-time that makes the universe accelerate in its expansion. And the Big Rip is something that happens if you have a particularly pathological version of dark energy. And I will say at the outset that we think it probably can't happen, in the sense that we think that the kind of dark energy you would need to make this happen probably doesn't exist in our universe, probably can't exist in our universe, but we can't be entirely sure. And some of the data are kind of pointing toward the possibility that maybe that kind of dark energy might have maybe happened at some point in the past, and probably isn't happening now, but we don't know for sure. So I'll just leave you with that, but it's probably not going to happen. But let me talk you through what it would be like. So I mentioned the cosmological constant. This was Einstein's idea that he put in that says that space has a little bit of stretchiness built into it. The reason that he came up with this idea is that he needed some reason why the universe had not already gravitationally collapsed on itself. So I'm going to make this argument with galaxies. He would have made it with stars because at the time we didn't know other galaxies existed. It works better with galaxies, so just bear with me. So here's the idea. There are galaxies in the universe, and there's gravity pulling them toward each other. Every galaxy is pulling on every other galaxy with gravity, and that should make them come together. In Einstein's time, it was thought that the universe was static, that it was unchanging, that everything was just there and not moving and not changing. There needed to be some reason why all the gravitation hadn't made everything fall together. There had to be something kind of holding it all up to keep it unchanging. So he put a term into the equation. It's called the cosmological constant. And what the cosmological constant does is it just kind of braces everything. It just kind of pushes, balances out the gravity, makes everything stable, right? It's not entirely stable in the sense that, like, it's kind of an unstable solution, but it was the best they could do at the time to explain why gravity hadn't pulled everything together already. Now, he got rid of it again, this term, because he found out that the universe is expanding, so the reason that everything's not falling together is that it's already moving apart, that the Big Bang created this expansion, things are moving apart, and that's the explanation. There was something that caused an initial push, and everything's just moving apart from everything else. And so he took the cosmological constant away and said we didn't need that term after all. But we do need something like it. If we're going to say that the universe is actually accelerating into its expansion, we need something that kind of pushes away. Now, if the universe has a cosmological constant, if the dark energy that's causing the acceleration is a cosmological constant, then it's constant because it's just built into space. And so, like, basically you'd have your cubic meter of space, and it's got a certain amount of cosmological constant in it, and like, that's just fixed. So even when the universe gets bigger, now you have sort of 2 cubic meters of space. Now you have twice as much cosmological constant, but the density of cosmological constant is always the same. It's just a certain amount per volume of space. So if we look at how everything in the universe evolves in terms of density, energy density versus time, so how much energy is contained in a volume as a function of time, then the different components of the universe act differently, right? So matter decreases as a function of time because the universe is getting bigger. If there's the same amount of matter, then the density has to be going down. Radiation also goes down. It actually goes down faster because not only is the radiation diffusing through the universe, it's also being stretched out to longer wavelengths, which is lower energies. So the energy density of radiation drops. But the cosmological constant is just constant, so it just stays the same, right? And so in this graph, we're about here. So we're at a situation where most of the energy density of the universe is whatever dark energy is. Let's say for the moment this is cosmological constant. And then some fraction is matter, and some very small fraction is radiation. But you can imagine that into the future, after a while, the matter and radiation will be completely unimportant, and everything's just a cosmological constant, right? That's when you get to a heat death, because everything else diffuses away and the cosmological constant does not. And I should say that, like, the nice thing about a cosmological constant is that, it is just constant. So all it does really is it moves things apart from each other. Like, the cosmological constant doesn't get more powerful over time or anything like that. It's just that, there's a lot of empty space in the universe, and then there's more empty space because things are getting pushed apart. But you could imagine a kind of dark energy that has a different property where it gets more powerful over time, or the density of it increases over time. You could imagine something like this. And that would be called phantom dark energy. And the difference between a cosmological constant and phantom dark energy is, in a cosmological constant version of the universe, every sort of volume of space has the same amount of cosmological constant in it all the time. So if that volume of space contains a galaxy, then it contains the same amount of cosmological constant, and the galaxy has already kind of won against the expansion. Like, the galaxy is already bound to itself, and it's going to stay bound to itself, right? It's the same way that, like, the universe is expanding, but this room is not expanding because there's a certain amount of cosmological constant in this room, and that's not getting bigger, right? The room has been built, it's stable, it's here, right? It's not being pulled apart from within. But if you had a kind of dark energy that was getting more powerful over time, or the energy density was increasing, then you could imagine a situation where the dark energy is building up within this room, and it would start kind of pushing on the walls, right? If you were in a galaxy and the dark energy were increasing in the galaxy, it would start to pull the stars off the edge of the galaxy. If you're in a solar system, it would start to pull the planets off the edge of the solar system. If you're on a planet, it would start to build up within the planet and start to pull that planet apart. And you can calculate that if you do have this kind of behavior with your dark energy, then at some point in the future, in a finite time, the dark energy will build up so much that it'll essentially rip apart the entire universe. And that's called the Big Rip. That's that event. Now, there are a couple of reasons that we think that this is unlikely. I mentioned before about these energy, so basically there's these energy conditions, there's reasons, theoretical reasons why we think that phantom dark energy probably doesn't work. But it is occasionally taken seriously as a possibility. And several years ago, there was a paper that came out talking about what would happen with phantom dark energy, and some folks at NASA made an animation of sort of the Big Rip to illustrate this paper that came out. And I just want to show you this animation. It's not what it would look like, but I think it's really cool that they did this. So you have the galaxies, and the expansion is going normal, and then, oh no. So to be clear, this is an official NASA animation. So that's not exactly what it would look like, but it would be very disruptive. It would be a problem. The good thing about the Big Rip is that we can calculate how far in the future it would be based on sort of the best measurements we have right now of what dark energy is doing. And the last time I checked, it's something like, it's at least 200 billion years away. And after 100 billion years, the universe is not interesting anymore anyway. As I showed you, you don't even see other galaxies. There's no cosmological microwave background to play with. It's just not that exciting a place. So if it's happening in 200 billion years, we're probably not around doing anything interesting. However, there is one possibility that could technically happen at any moment. So vacuum decay is an idea that's been around for kind of a long time. I think it was first discussed in kind of the 1970s. And it has to do with something called the Higgs field. Now, the Higgs field is a kind of energy field that's through all of space. And it has to do with how particles got their mass in the early universe. There's a story that goes on. There's actually, on Monday night, there's going to be a screening at the Princess Theater, I think, of a movie called Particle Fever, which is all about trying to find the Higgs boson, which is a really great movie. But it's about trying to find this particle that's associated with the Higgs field, this energy field that's through all of space. And the Higgs field has to do with, essentially what happened was in the very, very early universe, there was this energy field in the universe that had a different value than it has today. Okay, and I'll get a little bit more into the details in a bit, but essentially something changed in the very early universe that kind of set up how physics works. And that's why it was so important to find the Higgs boson, because it told us something about how our understanding of particle physics happened, how the particles that exist in our universe got the properties that they have today. Now, we have some tools to study the Higgs field. This is a view of a detector at the Large Hadron Collider. Large Hadron Collider is a giant particle collider in Europe. It has these particle detectors, and what happens is a proton comes this way, and another proton comes this way, and they meet in the middle, and they smash together, and a bunch of debris comes out, and it allows us to understand how particles interact with each other. This is one of the detectors. This is called CMS, compact muon solenoid. I took this picture at CERN a few years ago. Just to give you a sense of scale, there are 3 people in this circle. So it is a very large machine, and CMS is not even the biggest one. The biggest one is Atlas, which is larger. So you create these particle collisions, you look at the debris that comes out, and it helps you understand how particles interact with each other, what particles exist in the universe. And by doing a bunch of these collisions, in 2012, the Large Hadron Collider people managed to detect a Higgs boson. They detected a particle that is associated with this energy field that's throughout all of space, and that has something to do with creating the conditions for how particles work in our universe. Basically, the idea is that in the very early universe, before the Higgs field made this change, we had kind of different set of particles. They didn't have mass. Then the Higgs field changed, created the particles we know today, gave them mass, and allowed us to exist, basically. It created the conditions for the standard model of particle physics. This is the standard model of particle physics, except with the Higgs boson up there. So these are all the particles that we know exist in the universe that we have interacted with, that we found in detectors, that we're very sure are there. Okay, and I'm going to go through what these are because it'll be relevant to what we're saying next. So the sort of purpley blue ones over there, those are the quarks. So the quarks are they're components of particles called hadrons, like the proton and the neutron. There are 6 different flavors of quarks. There's the up, down, charm, strange, top, and bottom. They were named in the 60s and 70s. There was a lot going on at the time. So those are the quarks. Then in the green, these are the leptons. So we have the neutrinos, which are particles that are created in like nuclear reactions from the sun and other stars. And then there's the electron, muon, and tau particle. So muon and tau are kind of heavier cousins of the electron. The electron is, of course, the particle that goes around atoms, only that doesn't really circle like that. It kind of is in a sort of probability cloud of electronness. Won't get into that too much. And then in the red over there, those are called the gauge bosons. Those are the force carriers. Those are the things that mediate the forces of nature. So there's the photon, that's a kind of particle of light, and that's responsible for electromagnetism. So it's responsible for light, electricity, magnetism. There's the gluon, that's responsible for the strong nuclear force that holds the particles together inside the nucleus. And then there's the W and the Z bosons, and those have to do with, they're the mediators of the weak nuclear force, which has to do with things like radioactive decay, particles changing flavor, things like that. So by studying the properties of all these particles, and specifically by studying how they interact with the Higgs boson, we can learn something about what happened in the very early universe that created the conditions for the standard model of particle physics that we have today. And we can try and answer a question, which is, I think, a kind of important question, which is this question of, okay, the Higgs field changed in the early universe and created our lovely standard model of particle physics. Could that happen again? Could the Higgs field change again and totally mess up this picture? So people started to get really interested in this question when the Higgs boson was discovered. And this is a figure from a paper from 2012, shortly after the discovery was announced. And it's looking at the possibilities for the mass of the Higgs boson and the mass of the top quark. And the units here are giga-electron-volts. It's a unit of energy that we use for mass for particles. And basically, depending on how these masses compare to each other, you can have a situation where, the universe is stable, like it's definitely not going to change again. So if the Higgs mass is 100 and the top mass is 50, then the Higgs field is never going to change again. If the Higgs mass is 100 and the top mass is 200, then we're in a situation where probably the universe has already collapsed. You come over here and you get into a situation where the sort of mathematics is telling you something weird. So you might ask, where do we actually live? What are the measurements of the top mass and the Higgs mass? And the answer is there. So that's metastability, so stable for now. So metastability is like, it's fine, right? Like, it's not going anywhere. It's on the edge of the table. You'd have to do something to it to make it fall to the floor, right? But there's a real sense in which it would rather be on the floor, right? And you could imagine that something could happen to it and it would end up on the floor, and that would be bad, right? So to put this in sort of physicsy terms, So this is a figure from a paper from 1980 where they're talking about this possibility of what is called vacuum decay, where the Higgs field changes again. And this is the potential of the Higgs field. Basically, it's telling you about where the Higgs field would rather be, how it might evolve over time. But you can think of it for the moment, you can think of it as though these are sort of two valleys, and our universe is a little ball that lives in one of these valleys, okay? Now, there are two valleys, and one of them is higher up than the other one, in very much the same sense as the table here is higher than the floor. And so these represent different vacuum states, where a vacuum state is like the background state of physics in the universe. And if you have a situation like this, where one is a little higher than the other, then the higher one is called the false vacuum, the lower one is called the true vacuum. And there's a sense in which, we would, the universe would just rather be over there. And so the problem with living in a false vacuum is that you could imagine something could happen in the same way something could happen here, where the universe might move over to the other vacuum state. And that would be really bad because the true vacuum is a different sort of configuration of the Higgs field, meaning that particles interact in different ways. There are different kinds of particles, their masses are different, and you don't have the kind of atoms holding together that we are used to here. So on the bright side, we don't think that transition can really happen. We don't know how that would happen. In the same way, if you were a little ant trying to knock over my water bottle, you just wouldn't be able to do it. You're just not strong enough. That can't happen. However, we live in a universe that is fundamentally quantum mechanical. And one of the things you learn about in quantum mechanics is quantum tunneling. This is this idea that if you have a barrier and you put a particle on one side of the barrier and you wait long enough, eventually it'll be on the other side. It doesn't have to go through, it doesn't have to go around, it just kind of shows up over there. And there are a lot of ways to think about this, but you can think about it in terms of the uncertainty principle tells us we don't know exactly where the particle was anyway. Maybe it was just over there all along. And when you check again, that's where it is. It's really to do with the fact that the particle is described by a wave function, which is sort of this extended sort of probabilityness of where it could be, and it extends through the barrier. And so sometimes if you leave something alone long enough, it'll tunnel to somewhere else. When you learn quantum mechanics in undergrad or graduate school, they'll often tell you, if you put something on the table and wait long enough, eventually it'll tunnel through and fall to the floor. It's a really long time you have to wait, but in principle, that could happen. And unfortunately, the Higgs field is a quantum field, and so if you wait long enough, it will also tunnel to the true vacuum, if it is indeed in a false vacuum state. So what would that look like? Well, somewhere in the universe, the Higgs field would undergo a tunneling event. And to be clear, we can't predict when tunneling happens. If you put your particle on one side of a barrier, you can say something about, on average, how long you'd have to wait to check on the other side and definitely see it there, but you can't say for sure exactly when that transition is going to happen. So at some point, at random, somewhere in the universe, that transition occurs. And when it occurs, it creates a bubble. Basically, the Higgs field in one place kind of knocks down the Higgs field and all around it, and it creates a bubble of the true vacuum state. And so interior of this bubble, you have the true vacuum. The bubble wall is a kind of high energy shell that if it hit you would incinerate you. And then, of course, if you were inside the bubble, you would fall apart because your atoms would not hold together anymore because the true vacuum state is not a survivable state. Now, the bubble would appear, and then it would move outward at the speed of light, which means that if you were standing nearby, there is no way you're seeing it coming, because by the time the light from it gets to you, it is on top of you and you are destroyed. Now, in the 1980s, when Coleman and DeLucia were writing about this, they were the ones who made that plot with the potential. They were calculating what happens when this bubble appears. And they worked out that, at least for the model they were working with, the space inside the bubble, the true vacuum bubble, not only is one where your atoms don't hold together, but it's also gravitationally unstable, which means that first you get hit by the bubble wall and incinerated, then you fall into the bubble and your atoms fall apart, and then you get crushed into a black hole. And after they did that calculation, they wrote a little reflection on it. And I'm just going to share that with you because it's one of my favorite pieces of physics poetry that I've ever found. So this is from Coleman Solution 1980. And so they've just done this calculation, and they say, this is disheartening. The possibility that we are living in a false vacuum has never been a cheering one to contemplate. Vacuum decay is the ultimate ecological catastrophe. In a new vacuum, there are new constants of nature. After vacuum decay, not only is life as we know it impossible, so is chemistry as we know it. However, one could always draw stoic comfort from the possibility that perhaps, in the course of time, the new vacuum would sustain, if not life as we know it, at least some structures capable of knowing joy. This possibility has now been eliminated. So, I don't want you to worry about vacuum decay. I know that I told you it could happen at any moment, but let me just clarify a few things. So, first of all, what are you going to do? You can't stop it. And it would be painless. You wouldn't feel it would come so fast at the speed of light. Your nerve impulses don't travel that fast. You wouldn't feel it. You wouldn't notice. It would be, there's no tragic aftermath. But also, we can calculate based on our understanding of the standard model of particle physics about what we think that decay time is for the vacuum. And we get a really large number. It's something like 10 to the power of 100 or 500 years, which is a very long time. And so, even though technically it could happen anytime, the chance of that is just absolutely minimal. But the other thing that makes us think that we probably shouldn't worry about vacuum decay, again, there are other things you should worry about. But another thing is that the idea of vacuum decay being possible at all is really based on the idea that we totally understand the standard model of particle physics, and that there's no other physics that is going to change our understanding of how the universe works. And just to illustrate why we probably shouldn't rest on that, if we make a diagram of what the universe is made of, so about a quarter of it is something we call dark matter. And I haven't talked about that here, but it's mainly what I work on in my research. It's some kind of invisible stuff that holds galaxies together. We don't know what dark matter is, but that's most of the matter in the universe. And then there's dark energy, which again, we don't know what dark energy is, but it is most of the energy in the universe. And then there's just this little 5% slice that I've labeled here atoms, and that contains the entire standard model of particle physics. So dark matter is not in the standard model, dark energy is not in the standard model. So the idea that we really understand everything so much that we can extrapolate the vacuum decay and when it might happen and the fact that it's even possible is really hubris, right? There's a lot that we still don't understand. And understanding all this would give us some insights into the future of the cosmos. But for now, they are exciting mysteries, and we have a lot of work to do to figure it out. So I will just end there. Thank you very much.
Thank you. That was going to be my first request, actually.
Oh, I know. It's very stressful.
Yeah, thank you so much. Thank you, Katie. That was a fantastic talk.
Thank you.
All right, so we definitely have some time for some questions from the audience. So we have 2 microphones here in the auditorium for folks that want to ask a question from the audience. So we particularly encourage young people in the audience, if you have a question for our speaker, make your way up to the microphones. We've had several questions coming in online.
Okay.
So let's see. The first one that came in is in terms of this sort of big crunch. If you get a big crunch, do you then get another Big Bang?
That is a great question. Not necessarily. When you work out sort of the evolution of the universe possible, the evolution of space-time possible with Einstein's equations, there's a solution where it's expanding and there's a solution where it's contracting. But those equations do not give you any solution where it contracts and then bounces out again. You have to find some reason for that bounce to happen, something beyond general relativity, Einstein's equations. And it's actually kind of hard to get that to work out theoretically. So when I was in grad school, I was working with Professor Paul Steinhardt at Princeton, and he was working on models that would have a kind of compression and a bounce. And it's complicated. It's difficult. There are some bad things that happen if you try and get too close to the singularity and then come back. So not necessarily. A lot of people tell me that they like the idea of a big crunch because then you get a new universe. And it's like, well, maybe. We don't necessarily know. But in the book, I talk about some additional possibilities for the end that are cyclic models of the universe. And I talk about some of these ideas where you could have some kind of ending and then a new beginning. That's the secret fifth possibility that I didn't talk about here that you have to read the book to learn about.
Okay, that was one of the other questions.
Okay.
All right, go ahead.
You mentioned that one of the things that happens when the universe expands is that the wavelengths of light expand.
Yeah.
That causes them to lose energy. Is that correct?
Yeah. So yeah, each sort of photon loses energy in that process. Yeah.
Would that not include the possibility of then the universe just losing all of its energy and everything that's in it over time as a result of said energy loss?
So I'm not sure what you mean, like lose all its energy, like the energy
disappears. Is that correct?
Well, it gets stretched out, right? So if you think of the universe as a closed box and it gets bigger, there's the same amount of energy in it, just the energy density goes down. It's a little bit complicated actually with the light expansion. So how you work out conservation of energy in an expanding universe is actually kind of a matter of some debate. So it's not super straightforward where the energy goes in that scenario, because generally we think of sort of conservation of energy as something in a closed system, and the universe is not a closed system, right? So it's a little bit of a complicated question that I will refer you to others for that, because it's not something that, yeah, there are interesting articles written about it. But
Thank you very much. I appreciate it.
Sure.
All right, next question.
Firstly, good evening. It's a great honor and great pleasure to be here. And thank you, Emily, and thank you, Dr. Kate. My question is, we have studied 4 scenarios, possibilities. Is there a possibility that 1 or 2 scenarios can happen together at the same time?
Yeah, that's a great question. So I've thought about this a bit. So you could definitely have like essentially a heat death and then a big rip if the dark energy is like just a little bit worse than cosmological constant. It could happen that way. You could also have essentially a heat death and then vacuum decay if the vacuum decay takes long enough. And then there's the bouncing cosmologies, and some of those include like a heat death that then turns into a Big Bang, which I don't know, you can figure out what happens after that. But so there are some that you could kind of combine. Yeah, the sort of standard versions are I mean, it depends on if you think that the Higgs vacuum is really unstable, then vacuum decay is going to be inevitable eventually if the universe lasts long enough. So, yeah.
Thank you.
Sure.
All right, next question.
Good evening. I was wondering, so when we're talking about the universe expanding, I was wondering, is there like anything known about, like, what are we expanding into? What's beyond our, what's beyond our known universe? Are there more universes that are out there and are expanding in their own right? Like,
yeah, so that's a great question. So, I mean, the short answer is we have an observable universe in the sense that, like, there's a volume out beyond which we cannot see. I mentioned that if you look far enough in any direction, you see the cosmomicrowave background. Just a little bit beyond that is a point where it's so far away that the light, if it were traveling to us from there, would take the entire age of the universe to get to us. So you can imagine there's a point a little beyond that where the light can't have gotten to us. there has not been enough time. And that defines our observable universe. It's called a particle horizon. That's the distance out to which we can see. And we can't see whatever might be beyond that. We're pretty sure the universe keeps going beyond the horizon because there doesn't seem to be anything different about those distant places. So we're pretty sure it keeps going for a very long time, and a very long way. And there are early universe scenarios that we think suggest that it's like much, much bigger than our observable universe. But we don't know for sure. So what we see, what we observe, is that the volume that we're in, things are getting farther apart. It's kind of like if you're leaving a concert or something and it's very crowded and you just see a crowd around you, and over time the crowd is kind of thinning out, but you can't see where they're going because you can't see beyond the people around you in the crowd. It's kind of like that. Like, we can see that the galaxies are getting farther away, but we can't see like if they're going somewhere in particular. We just see that the matter density is going down, essentially. We don't have any evidence that the universe curves around. We don't have any evidence that it's finite in any way, but we really don't know. There could be some kind of larger space that we're embedded in, we're not sure. But there's an analogy I sometimes use about the expansion of the universe, which is that the universe is expanding like your mind is expanding. It's not expanding into anything, you're just getting less dense.
Thank you very much.
So you can also leave here tonight with a joke to tell your friends. All right, so one more final question that came in from online. So you mentioned that when Einstein formulated his theory of gravity, he didn't know that other galaxies existed.
Yeah.
First of all, that's like a little bit mind-blowing.
Yeah.
But the question is sort of, what was it like when he found out that did it change his theories of gravity?
I don't know. The pieces of evidence that were used to confirm general relativity, Einstein's theory of gravity, involved solar system measurements and also gravitational lensing. So they involved looking at how Mercury was going around the sun. They involved looking at how light is bent around the sun when, during a solar eclipse, and you can see that the positions of stars are different because, Einstein's whole thing is that gravity is the bending of space. So it wasn't relying on extragalactic information. But yeah, I don't know. I think that it changed sort of the way that you can formulate the evolution of space-time itself in some way. But yeah, I don't know what it was like to be at that time. I mean, at the time there were all these arguments about what are called these the nebulae, the island universes, these sort of fuzzy things in the sky. Is that a collection of gas, or is that a whole other galaxy? And people were arguing back and forth. So this was sort of between 1900 and 1920 was when all these discussions were happening. Yeah, I don't know. I don't know what it must have been a wild time.
All right, and if there are no more questions in the audience, let's thank our speaker again. Please join me in thanking Dr. Katie Mack.
Thank you. Thank you.